This is video number 1 for Exam 5 for Math 107. In the first problem on this exam, you are given the order of a matrix. In this case, it's 3 by 2. Now I can write something. Okay, it's 3 by 2. You're given that. And the important thing to remember is which is the number of rows and which is the number of columns. Rows first, then the number of columns. So this would be a matrix that has 3 rows, say 1, 2, 3, but only 2 columns. Here's one column, here's the second column. Then you're supposed to write the placeholder for the coefficients as A with subscripts. The subscripts give you the row and then the column number again in that order. So in this case, we would have, it's a 3 by 2, so you've got A1, 1. That's first row, first column. A1, 2, first row, second column. A2, 1, second row, first column. A2, 2, second row, second column. And the last is A3, 1, which is the third row, first column. And A3, 2, third row, second column. Then the matrix is enclosed in square brackets. It should look just like this, unless of course the order is different, and then you make the adjustments that you need. In this case, we're given a matrix. This is one of the Pauli matrices. I'm going to tell you what the other Pauli matrices are, and this is a hint, and as good students you know that a hint on a test is more than just a hint. You might see these again. Okay, here's the next one, or one of them, the second one in our list here, and the third one is like this. So here are your 3 Pauli matrices. These are matrices from physics, and you'll notice what this one has in it are i's. I is, yes, that's the imaginary I equaling the square root of -1. So this is practiced not just with matrices but also with the complex numbers. Here you need to square this Pauli matrix. So I write the Pauli matrix like this. And then I write the next one afterwards because I'm squaring it, multiplying it by itself. Now you really need to know matrix multiplication, and sometimes some very good students miss this. So let me go over it a little bit. I'm going to multiply these 2 matrices together. To do that, I take the first row of the first matrix and multiply it against the first column of the second matrix. So I'll have 0 times 0 plus -I times I. That's -I squared. Now I take that first row again and go against the second column. 0 times -I, 0. -I times 0, 0. So all we get over here is a 0. Now go back and take the second row and go against the first column. I times 0 is 0. 0 times I is 0. So this result is a 0. Then I take that second row again, this row right here, and I go against the second column. I times -I is -I squared, and then 0 times 0 is 0. So here I have -I squared again. Now you don't leave it like this, you go ahead and evaluate it. Remember that I is the square root of -1. I squared is -1. So substituting that, you have negative of a -1 is +1, and then again another 1. This matrix is the identity matrix, and because it's the identity matrix, this means that the 2 matrices who multiply together to give the identity are inverses of each other. This means, and this is one question for the test, is that the Pauli matrix, in fact all of them, is the inverse of itself. Its own inverse. What does this mean in practice? Think of this matrix as transforming something. Say you have some kind of shape, like a box, okay, and you apply this matrix, and this matrix tells you how to rotate and turn it in space. And say you just leave it on a table and rotate it 180 degrees. Okay, that was the application of the matrix. Now if you apply the matrix again and rotate it another 180, it will come back to be in exactly the same configuration that you started with. You see how that would be the inverse of itself? Okay. Be sure you know how to square these matrices too. In this question, you're asked to write as a matrix equation. A matrix equation has an equal sign. And then you have to identify the solution vector, the coefficient matrix, okay? And you should also identify the vector of unknowns. So to construct this matrix equation, all the coefficients, first of all, the equations have to be written so that the constants are on this side. See the constants 12, 10, 4, and 7 are on the right-hand side of the equal sign. So here's your equal sign, and here are all those coefficients right there, lined up. Okay, let's see. Now, to make, that would be your solution vector. A matrix that has either one row or one column is called a vector. Okay. And now we're back to working on the coefficient matrix. The coefficients are the numbers multiplying the variables. So here's your 4, a 5, a minus 3, and a 2, and those make up the first row. In this case, there is no x term, so you have to put a 0, and then the 5, 2, and then minus means minus 1. The next row is 30 minus 6, 1, and 1. If nothing's here, remember that is a 1. It's the old invisible 1. So the coefficient is 1, not 0. It's 0 in this case because there are no x's. Okay. And the last one, you've got 9x, so the 9's here, no y's, so you have a in this question, you're to write the matrix equation. And a matrix equation has an equal sign. Right. So you construct a matrix equation. It's going to consist of the coefficient matrix, and that's this matrix right here. Then there's a vector of unknowns. That's your x, y, z, and t's, or x1, x2, x3, whatever the variables are. And then you have, I'll show us red, I guess, the solution vector. Important thing is to make sure the equation is ordered properly so that you have x, y, z, and t lined up. And if there is no x, for example, in this particular case, there's no x, there really is 0x, and so you put a 0 in the matrix, in the coefficient matrix. In this last line, there's 9x, but there's no y's, there are no z's, and there's a minus t. So the coefficient is 9, then 0, 0 for the absence of y and z, and then of course t is multiplied by negative 1. Remember here in this case, the second and the third line, there's really a 1. It's 1z and 1t. You have to put the 1 in. If you put 0, you'll end up with just 30x minus 6y equals 4. And you don't want that. You want 1z and 1t, so you put the 1's in there. This is a Gauss-Jordan, but you're walked through the Gauss-Jordan, and you have to know how to apply these steps. And one error that I see is that when you're given these, alright, perhaps it isn't clear the way it's written, so let me go over that. You're given an initial augmented matrix. And remember, augmented matrix had, here was a solution vector, I'm sorry, there was a coefficient matrix and the solution vector, and they're put together. So you start right with that, and you do a row operation. Take row 2, divide by 6, and stick the result back into row 2. Alright, so I'm going to try that right over here. I take row 2 and I divide by 6. So here's row 2. So 0 divided by 6 is still 0. Okay, there's a 0 there. 6 over 6 is a 1. Here's the 1. 3 over 6 is a half. So that's right here. And you have a minus 6 divided by 6 is the minus 1. And that's right here. Now, you do this calculation over here, you take the results and you store it back into row 2. Now, when you go to this next one, which says take row 3 minus 4 times row 1 and put the results in row 3, you don't go back to the original matrix. You don't go all the way back here. Instead, you just use this one and advance. So the first row stays the same, 1, 2, 2, 9. The second row, 0, 1, a half, minus 1, stays the same. But for row 3, you take whatever was originally in row 3, and you subtract from it 4 times row 1. Well, you should write it out, but you can just do it here. 4 times row 1 would be 4 up here, minus 4. That would give me a 0. Now I have 0 minus 4 times a 2 is 8, so there's the minus 8. Now I have a 3 minus 4 times 2 is 8, so 3 minus 8, there's the negative 5. And for the last case, you have 7 minus 36, because that's 4 times 9, and you get the negative 27. So you've constructed the matrix in problem 5 using the matrix results in problem 4.